Hello everyone. Today in geometry we will be looking at something called geometric mean but in a right triangle. So previously we talked about what is a geometric mean in an algebra sense, where it's kind of like quote unquote the average of two numbers when multiplied together in order to get the ones in between. So now we're looking at geometric mean, and where does it come in geometry, and more specifically in a right triangle. So here in the picture below, you will see that we have a right triangle. We have where the leg is going to be A, we have leg which is going to be B, and we have the leg which is going to be C. Now, in addition to that, we're going to take this right triangle and break it into a few components. Notice that I have introduced h over here, which is the altitude to the hypotenuse because it is perpendicular to it. And from where the altitude and also the hypotenuse connects, you're going to see two segments that the hypotenuse will break into. That is going to be x, and then there is going to be y right there. So it turns out that when you take the triangle and break it into two triangles like this, or I'm sorry, more specifically, whenever you have a right triangle and you break it into two other right triangles, like so, according to the altitude of the hypotenuse, there is a relationship between those two, and actually there's a relationship between those three triangles that we have. So first of all, you'll notice that on the left, I have identified that as kind of like a gray triangle, and then I also have the pink triangle that's on the right, and then the final triangle is the whole thing itself. The relationship is that those three triangles are all similar to each other. Okay, repeat it one more time. Those three triangles, the pink one, the gray one, and the big one, they are all similar to each other. And here is how we can kind of do like a quick proof of that, just to show you that they are similar. So notice that all of these three triangles, they all have right angles. So that's one thing that they have in common. If I can find that they have another angle that's the same, then we're pretty much home free. So let's do this then. Let me go ahead and go to this corner over here, and we're going to go ahead and denote that as angle. We'll go ahead and use a new symbol. We'll call theta for right now. Okay. Now, if that is angle theta, then let me go over here and go ahead and say that this guy is going to be 90 minus theta. And that is because over here we have a right angle. Now, since we have that right triangle, then that's 90 minus theta. And right next to it in that lower right-hand corner, since one of the angle is 90 minus theta, then the one next to it is its complement, which tells me that it's theta once again. And finally, if we go to the very, very top, then this angle over here should then be 90 minus theta because of the gray triangle. And in addition to the original triangle, you have a right triangle to begin with. So if the original angle was theta, then this definitely has to be 90 minus theta. So you can see where all these three triangles are actually similar to each other by the AA similarity. Okay. Now, that means that we can actually set up some sort of proportionality with them. So that's what I'm going to show you underneath right now. So here we have the three triangles. We have the original one, the big one over here. We'll go ahead and call that triangle number one. The other one, we're going to go ahead and call triangle number two, the gray one. And then the last one will be triangle number three, which is the pink one. So what I'm going to do is I'm going to look at each triangle, look at the variable that they have in common, and set up a proportionality. Okay, so for example, in the case of triangle number one and triangle number two, I noticed that they both have the variable a in common. So then that means I'm going to see if I can set up something with that. So according to my proportionality, then I can say that a over, let's see, c is going to be equal to x over a, right? Because it's going to be this side over this side is equal to this side over this side over here. Okay, so that's just one proportionality you can set up, and you can definitely set up some other ones. But this one is the one that is specifically telling me a story, because if you notice the proportionality that I set up right here, A is a geometric mean because of the way that it's written. Okay, A is a geometric mean between sides C and X. Well, let's go ahead and move into triangle 2 and triangle 3 and see if we can do the same thing. Notice in triangle 2 and triangle 3, let me just go ahead and redraw this in a little bit. Okay, let's see what variable they have in common. I'm noticing that they have h as a variable that's in common, so maybe we can set up then something with that one then. So similarly, we can say that x over h is equal to h over y in triangle 2 and triangle 3 respectively. And hey, if you notice that right there, h is now going to be a geometric mean with x and y, the two variables. And finally, for triangle number 1 and triangle number 3, looking at what they have in common, I'm noticing side B is what they have in common. So then that means we're going to go ahead and set up some sort of similarity with those two. Let's see. Looks like we're going to use C over B is equal to B over Y. And hey, as you know it, B is then a geometric mean with C and Y then. Just like in the middle one, H is the geometric mean with X and Y. So in the grand scheme of things, if I put it all together so you can see it a little bit better, here is what's happening in the big picture. So in the first proportionality, you can see how A is the geometric mean with X and Y. Actually, it's X and C in this case. I think I called it C, so I messed up on that one. Let me go ahead and change this guy over here. C is going to be the hypotenuse here. Okay, so X and C, which is the hypotenuse. And we'll just go ahead and make that a little bit bolder. Okay, so you can see the relationship there. Then in my second triangle, H is the geometric mean, which I denoted in red. And then you can see what its geometric mean with respect to. And then finally, B is going to be the geometric mean in the third equation. And it's going to be a geometric mean with C and Y then. So in terms of which ones are going to be the geometric mean, it turns out that A and B, the legs, and also the altitudes are going to be the geometric means. In terms of what they are the geometric mean to, it looks like it's always going to be something related to the hypotenuse. So it's either the hypotenuse and the segment next to it, or the segments that's broken up by the hypotenuse because of the altitude. So this is going to be something that you might want to memorize then as the geometric mean for right triangle. All right, so let's go ahead and see if we can apply this to some of these problems below so you can see how this actually works out. So here in this example, you'll notice that we have a right triangle where its altitude to the hypotenuse is drawn, and we have three segments that are missing, x, y, and z, and I would like to solve for them using this geometric mean thing. So first, let's go ahead and set up what we can. Now, we can set up three different equations. I would like to usually solve for or set up the equation that I can solve for first. The first one I can solve for is going to be y over here because y is the geometric mean to the two segments that are going to make up the hypotenuse. And in terms of how that works, it's going to be 27 over y is equal to y over 3. So you can see how we can solve for y over there and then go ahead and, get the numerical answer out of this then. So let's see, this is going to give me y squared is equal to 27 multiplied by 3, which is the same thing as 3 to the 4th power or equal to 81. So that tells me that y is going to be equal to 9. And as soon as you have this, we can go ahead and set up the other parts then. So this time, let's go ahead and solve for z then, okay? Or you can solve for x, doesn't really matter. So in the second equation, then z is going to be the geometric mean to the side that's next to it on the hypotenuse, which is 3. And then be careful over here, the whole hypotenuse, which is going to be 30 because 27 plus 3. So now we can solve for what z is equal to. So let's see here. Then that means that z squared is equal to 3 times 30, which is equal to 90 then. So then that means that z is going to be equal to the square root of 90. And this is probably where you're going to have to reduce or simplify this as much as possible, just to make sure the answers are going to come out nice. And maybe you can combine it with other stuff in the future. So z is equal to the square root of 9 multiplied by the square root of 10. So z is going to be equal to 3 multiplied by root 10 then. And finally, for the last one, we're going to go ahead and set up x. So let's go ahead and maybe use black for this guy right here. So it looks like x is going to be the geometric mean to what? Well, the side that's next to it on the hypotenuse, which is 27. And then also the entire hypotenuse, which is going to be 30. So then that means that x squared is equal to 27 multiplied by 30. And well, before we multiply all this out, let's just go ahead and see if we can make this a little bit easier for us. 27, that is going to be 3 to the third, multiplied by 3, multiplied by 10. So x squared is equal to 3 to the fourth, multiplied by 10. So if I take the square root of both sides, then that means now that we have the square root of 10 multiplied by 3 to the fourth raised to the square root. Well, that's going to be equal to 3 squared, which is equal to 9. So then that means the answer for x is going to be 9 root 10 then. So finally put it all together, 9 root 10 over here. And then this guy over here is z, which is going to be equal to 3 root 10. And then finally, y, which is going to be equal to 9 then. Okay. All right, let's try one more example with this one, and then we'll do one with the proof. Here is going to be kind of the same idea then. Okay, so let me go ahead and make a little bit of space just so that we can go ahead and get started. Just like before, I want to solve for in this right triangle with the altitude to the hypotenuse. What are the lengths A, B, and C? So let's go ahead and set up the the proportionality according to the geometric mean then. So looking at this, it looks like I can solve for B first. Okay, it looks like I can solve for B first. Now, if you can't quite see which variable you can solve for first, what you can do is set up each proportionality just to see which one only has one variable in it, because that's the one you can usually solve for. So here we have 12, which is the geometric mean. To the sides that are next, the side that's next to it on the hypotenuse, which is going to be 4. And then with b in there, it's going to be 4 plus b. So this one is a little bit more tricky, but we can definitely solve for this still. So let's see, 4 multiplied by 4 plus b is equal to 12 multiplied by 12. So we're going to go ahead and divide each side by 4, giving us 3 over here. So it looks like 4 plus b is equal to 36. So then that means that b is equal to 32. Okay, next we're going to go ahead and set up another geometric mean. Now let's go ahead and see if we can solve for a over here. Okay, now let's just say that, as we said earlier, you didn't know which one to set up. If you were to set up a geometric mean with a without solving for b, this is what it would look like. A is the geometric mean to 4 and b. So notice here we cannot quite solve for this equation because we don't have two equations, two unknown. But since we solved for b already, then now I can go ahead and make a substitution and then go ahead and solve for it. Okay, so sometimes you're going to have to kind of like play around with these three equations to see which one you can solve for first, to kind of put your foot into the door and then solve for the other ones. So let's see here. Then that means that a squared is equal to 4 multiplied by 32. And let's see, a squared would then equal to 4 times 4 times, looks like 8 in this case. Can we make this a little bit nicer? Sure, we can say 4 squared multiplied by 8, which I'm going to write as 2 squared multiplied by 2. So this thing right here, that used to be the 8 right here. And I'm writing it in this form, so then that way you can see what happens if I take the square root then. So take the square root of both sides. The square root of 4 squared, well, that becomes a 4. The square root of 2 squared, well, that becomes a 2. And then finally, we have a root 2. So that means that a is going to be equal to 8 root 2 then. Okay. Finally, we'll go ahead and set up the last one, which is going to be c. So let's see. I'm going to go ahead and use maybe like say gray for this one. Or actually, green for this one. Okay, so C is going to be the geometric mean to B, and then that means that the other part is going to be the entire hypotenuse, which is B plus 4. We know what B is, so then that means we can make it a little bit easier by plugging in the missing parts. So that means that 32 divided by C is equal to C divided by 32 plus 4, which is equal to 36. So go ahead and cross multiply. So c squared is equal to 32 multiplied by 36. So let's see, c squared is equal to, kind of running out of space, 36, I see it as 6 squared. 32, I see it as 2 multiplied by 4 squared, which is 16. So if I take the square root of both sides, then that means that c is equal to the square root of 2 multiplied by 4 multiplied by 6. So c finally is equal to 24 root 2. Okay, so there it is. That's going to be our answer for C. And just kind of like a word of precaution, I usually like to write it so that it's square root at the end, not square root before, because whenever you write it as like square root of 2 multiplied by like say an integer, sometimes what happens is that people, kind of like write the square root a little too long, and then as a result, the reader does not know if the square root is going to contain the next number or not. So just to make it a little bit easier or more distinct, writing the whole number first and then the square root term afterward, it would be more ideal then. Okay. All right, so now let's go ahead and look at this last one right here, which says that if you have a rectangle below, okay, so given the rectangle, oops, sorry, let's go ahead and make this a little bit bigger so you can get more in there. Given the rectangle below is inscribed inside a right triangle with its diagonal as the altitude of the hypotenuse. So here you can see that we have our rectangle over here because of all the right angles. And the diagonal right here is going to be the altitude to the hypotenuse of this right triangle that is going to be inscribed in it. What I want to do is I want to prove that the area of the rectangle is going to be the following equation over here. Square root of a times b times x times y, where you can see where a, b, x, and y are located. All right, so let's first start with what we do know. The area of a rectangle is simply, according to this picture, base times height, which is going to be b multiplied by x, which in this case seems pretty simple. The question is, well then, how do I take this and break it into these guys over here? Well, if you notice, we actually have a lot of geometric means that we can set up and other locations where we can see other variables. And here is one of them. X, because this is a hypotenuse, x because this is a rectangle, is also located over here. And as soon as I write x over there, you'll notice that x would then be the geometric mean to A and B. So what that means is that x is going to be a geometric mean. Let's go ahead and set that up on the side. X is the geometric mean to A and B. So from here, we can say that x squared is equal to a times b. So x is equal to the square root of a times b. So, you can see that this is your formal definition according to algebra. So we can go ahead and write it this way. Or if you want, you can derive it like what I did. But nonetheless, x can be replaced by the square root of a times b. Now, with this b over here, you're thinking, okay, well, that's just going to not give me much, but it looks like b, I can do the same thing and write it over here. And if I do so, then that means that b is now the geometric mean to this guy over here and this guy over here, because it looks like b is the altitude to the hypotenuse of the right triangle on the right. So in this case, b is a geometric mean. Then that means that b is equal to the square root of x times y, just to kind of save you a little bit of time, just like last time, because you can see my pen's running out of battery, so I need to make this one quick. So if I make that substitution, then that means that's going to be equal to the square root of x times y. And right there, we put it all inside the square root, and that's where the a, b, x, y actually comes in then. All right, so thank you so much for watching. I will see you guys next time then. Have a good one. Goodbye.